So today's video we're going to cover adding and subtracting radicals and radical expressions. So our main idea today is really about combining like terms, and we have some things that we know from before that we can use to help us combine radicals. So the most important thing to remind yourself today, when we write a mathematical expression, the number that comes first, we call that the coefficient. And that answers the question, how many of something do we have? So for example, this 3 here represents we have 3 of something. Then in math, the thing that comes after it, the label that comes after it, so we'll call it the label, that answers the question of what? So if we look at the first example, here I have 3 feet, and I'm going to add 6 more, right? I have 6 of something, and what do I have 6 of? Well, I have 6 feet. So in the end, I should have 9 total feet. So what that tells us is what I'm summarizing down here. When we combine terms, they have to have the same label. So I could combine 3 feet and 6 feet because they both were indicating with feet. And when we combine like terms, all we really do is combine their coefficients. So I took 3 plus 6 and that gave me 9. And their labels will never change. If I start with feet and I add more feet, I should have feet at the end. So we've seen labels in math in other ways. They're not always nice words like feet, inches, or something that we might recognize. Sometimes they're just letters. So -4, that would indicate how many of something I have. And what are those things? Well, they're called x's. And I'm trying to subtract 7 of those same exact things. So my answer then, well, if I have -4 of something and I'm taking more away, I would have -11, and whatever those things were, I called them x's. We talked about polynomials, right? So here I have 5 halves of something that I've called x squareds, and I'm going to add 1/2 of something that I've also called x squared. So in total, 1/2 plus 5 halves is 6 halves. And what did I call those things? I called them x squareds. Now, this brings up another important point when we combine like terms. Sometimes we need to simplify, right? 6/2, we could just rewrite that as 3x squared. So a little kind of note here to ourselves is we always simplify our answer. Now, our last example brings us to actually adding or subtracting radicals. So when we look at a radical expression, I have 3, and what did I call these things? Well, I called them the square roots of 2, and I'm trying to add 5 of those same exact things. So I hope that you're starting to see intuitively that if I had 3 of something and I added 5 more of those same things, I should have 8 of those things. And what were they? Well, they were called the square roots of 2. So just to be very explicit, I've just recopied that example. So what we want to make sure of is that when we work with terms with radicals in them, we know that they are only considered to be like terms, meaning they can add them, if the number under the radical is exactly the same in whatever we're trying to combine. So here, since this label, square root of 2, or in other words, the 2 is the same as this 2, since these labels were the same, again, that told us we could combine their coefficients and keep the labels the same. So let's go through our first example that'll actually look a little more similar to the type of problems you'll do in math class. So we need to combine these terms. What I have copied over on the left side, which will appear on all the examples we do, just so you're aware, is I have a reminder about what we've been talking about. When we combine like terms, they have to have the same label. When we do combine them, we just change their coefficients. Our labels never change. But we always write our answer in simple form. So here's going to be our list of steps for working with radicals by adding and subtracting them. So I also reminded us that radicals are only like terms if the number under the radical sign, which we call the radicand, is exactly the same number. So like on this example, our easiest example, we're going to ask ourselves, are these like terms? So what we mean by that is the label here is the square root of 2, and this label is also the square root of 2. So here I have 3 of the square roots of 2, and I'm trying to add 4 of the square roots of 2. So yes, they are the same because they have the same label. So if I have 3 of something and I try to add 4 more of that same thing, I should have 7. And what am I adding together? What are these things called? They're called the square roots of 2. And that answer is done. And obviously we know it's done because there are no perfect square factors that would go into the number 2. Before we move on to our next example involving radicals, it's important to remind ourselves of something we know about combining other like terms. So here I have an example of a fraction, and something that's important about a fraction is we can see the denominator of the fraction is the label of this term. It's the size of the original whole. And the top, the numerator, is the coefficient. It tells us how many of this size piece we have. So I have one of this size piece. So on the other fraction, I would notice right now that the label is a 4 and the coefficient is a 3. So this tells me I have 3 of the size of the pieces that we've called fourths. So I have 3 of the fourths, and here I have 1 of the halves. These labels are not the same. What we had originally said was when we combine like terms, they must have the same label. But sometimes we might need to rewrite one of the terms so that they do have the same label. So for example, I could rewrite 1/2 as the number 2/4. So then when I consider their labels on the denominators, fourths and fourths are the same label. So when we add like terms, we never change their label. That's why they're still fourths. And if I ask myself, well, how many fourths do I have? I had 2 of them here and 3 of them there. So in total, I should then have 5 of them. So again, what we'll start to see is when we combine like terms, we might need to rewrite some of them first. So again, when we move on to example number 2 here with our radicals, when I look at these originally, the first thing we would check to see is that they do not have the same number under the square roots. So right now, they are not like terms. What that means is we might need to rewrite one or maybe both of the terms so that they could be like terms. So when I look at the first term, there is no way for me to write the square root of 3 because it does not have any perfect square factors. But instead of the square root of 12, I could have written that as 4 times 3. So if there's 2 numbers multiplied under one square root, I could give them each their own square root, which is a product property. I'm just going to rewrite that and rewrite my plus sign. But the square root of 4 is just 2, and then I have times the square root of 3. So after I rewrote the square roots, now the square root of 3 and the square root of 3 are the same label. So if I had 3 of them and I added 2 more of them, in the end, I should have 5 of them. And the things that we're speaking of are called the square roots of 3. In example number 3, the first thing that we should know when we're trying to add or subtract radicals is that they need to have the same number under the square root in order for them to be like terms. So again, here what we notice on this one, this is the square root of 27, and this is the square root of 48. Those are not the same numbers under the square root, so they are not like terms, so we need to rewrite them. So I'm going to rewrite my negative. Now instead of 27, I need to rewrite that using a perfect square. So I'm just checking my perfect squares like 4, 9, 16, 25, 36, 49, so on and so forth. So with 27, I'm going to use 9 times 3. With 48, the biggest perfect square that goes into it is 16. So I could rewrite that as 16 times 3. So with the negative, that just stays out front. If 2 numbers were multiplied under one square root, they each could get their own square root. So I will apply that twice. And then I will simplify the square root. So here our negative is just a coefficient. So we have negative times 3 root 3 plus 4 root 3. So now when we compare their labels, the square root of 3 and the square root of 3 are the same. So if I had negative 3 of those things and I added 4 of those things in the end, I would have 1 of those square roots of 3, which of course you could just rewrite without the 1 as the square root of 3. Now the last reminder example, per se, something that will give us some background information, is the last thing that we've said here. Some terms just cannot be combined in any way. So when I look at some of these terms and I compare their labels, this is x squared, that label is x squared, and this label is x. So these two are like terms because they have the same label of x squared. So if I had 3 of them and I added 5 of them, in total, I would have 8 of them. And what I'm speaking of, we called x squareds. Now, this is not the same label. So it is not a like term. So I can't combine it. So my final answer, or if I just write it in black here, is going to have 2 terms. because some terms just cannot be combined in any way. So we're going to see that with radicals on our next example. So our last example involved just a few more terms, but the first thing we should check to see when we're combining is if anything has the same label. So this has a label of root 3, this has a label of root 24, this label has root 27, and this label is root 54. So the first thing that we should notice is right now there are no like terms. None of the numbers under the radical are the same. But that doesn't always mean that we can't do anything. This may require us to rewrite them. So we should go ahead and try to rewrite as many of these as we can. So I'm going to put my term separators in just so I have a little more organization. So I'm going to start with this first term here, which I'll highlight in that black color. And the reason this one I'm going to start first is just because there's no way to simplify it. There is no perfect square that goes into 3. So this is going to stay 6 times the square root of 3. So moving over to the next term, the second term, which I'm highlighting here in purple. This one we will be able to write in a different way. So I'm just going to copy the plus 5. Now instead of 24, we should find the biggest perfect square that goes into 24. So I'm just reminding myself of the perfect square, like 2 squared is 4, 3 squared is 9, 5 squared, and then 6 squared, and 7 squared. So the biggest perfect square that goes into 24 is 4, and that'd be 4 times 6. So if there's 2 numbers multiplied under one square root, they each can have their own square root. The square root of 4, of course, is 2. And then we have the square root of 6. So 5 times 2 is 10 square roots of 6. I'm keeping the plus there so I know that I'm adding that, just again, because that's the original up there. So we're moving on to our third term, which I'm going to do in this orange color here. So for our third term, I'm going to copy the negative 3, and I would see from up here that the biggest perfect square that goes into 27 is 9 times 3. So if 2 numbers are multiplied under one square root, they each can have their own. The square root of 9 is 3, and then negative 3 times 3 is negative 9 square roots of 3. We're going to continue, and we'll just simplify the last term very quickly, which I'm going to do in a green color just to keep track of it. So I'll copy my plus 4. Now instead of 54, I'm going to write that as 9 times 6. And then we'll use the product rule to rewrite it as the square root of 9 times the square root of 6. Square root of 9 is, of course, 3. So we have plus 12 root 6. So after we rewrote some of the terms, we can now combine a lot of them. So we can see that this label, the square root of 3, is the same as this label, the square root of 3. So if I had 6 of them and I subtracted 9 of them, which I'm going to write 6 root 3 minus 9 root 3, that of course would give us negative 3 square roots of 3. Looking at the terms that are left over, this has a label of root 6, and so does this. So if there was positive 10 of them there and positive 12 of them, or as I'm rearranging it down here in black, I could rewrite this as plus 10 square roots of 6 plus 12 square roots of 6. So if I had 10 of them and I added 12 more of them, of course, I would have 22 of those square roots of 6.